Good morning, ladies and gentlemen of
Good morning,
calculus.
Mr. G.
Good to have you. Good to hear good news from a lot of you. Carson, that was really good news about your applications. Your ACT scores, really, really good.
He got an 87, just for you at home wondering.
Yeah, so it's, I don't know if he's still gonna work and do some more work for a perfect 36, but he's not that far off.
He got an 87.
Okay, here we have let f be a function that is differentiable in the interval. And so if a function is differentiable, what is it also that's necessary?
Continue.
Continuous by default, since differentiable is all I have to say. On 1 to 10, and so how did you work this problem already?
Yeah, I just did it in my head.
You did it in your
I
head?
mean, I was just able to like picture the graph and then went from there.
Did you picture the graph in your head? Did anybody actually draw the picture, sketch the picture on there?
No.
You didn't?
It does like.
Well, how do you, I don't understand how you would do that without sketching
Well,
a picture on this.
If it looks like that, it would do something like that.
Yeah, that's right. So Aaron is let me tell you what Aaron is sketching here. He's sketching something that looks like this. Something like this, right?
Yes.
Yeah, so what he has is that from 1 to 10, if f of 2 equals -5, so here we say f of 2, so here's 2, and f of 2 is -5, so we have 2 comma -5. Would that be right? And then f of 5 equals 5, so here's f of 5 equals 5. So we'll say that would be 5 comma 5, right? And then f of 9 equals -5, so here at 9, we're back here at -5. So I put 9 comma -5. And so which of the following must be true? Now does it have to take this type of turn here? You don't know what it is, right? It could be like right? You don't know exactly what it looks like, but you know that it meets these points. And so what can you say for this? Does f have at least 2 zeros?
Yes.
Why do we know that?
Because they're right there.
And
Because it has to go.
what theorem do we use to prove that?
Oh, it was. I'm not gonna remember it.
What did you say you were about to say it, Hannah? What was it?
No, I definitely was about to say it. I was just being a smart aleck answer.
Is it the one talking about the Pauli one?
I'm on it.
Yes, intermediate value theorem, okay?
Yeah.
Intermediate value. I was right there.
Intermediate value theorem. The graph of f has at least one horizontal tangent. Is that true?
Just say it.
Yes.
That is true, okay?
It has to go
Why?
like back down.
Why? Because of what? Because of what? What tells us that has to be the case?
That'd be Rolle's theorem.
That'd be Rolle's theorem, which is a subset of intermediate value theorem. So you could say Rolle's theorem like Aaron did, or mean value theorem, which is the bigger tent that includes Rolle's theorem. And thirdly, for some c between 2 and 5, f of c equals 3. Is that correct?
Yes.
Why is that correct?
Because it has to pass through 3 to get to 5.
Yeah, so 3 somehow, and that's going to be also IVT, right?
Yeah.
So this is, I like this problem because it kind of puts these different things together. And to me, Aaron said he drew this picture in his head. Well, I probably could do that, but I like to just draw a little sketch like that, just to see where it is, and then you just kind of figure out where things are, and then it's a real easy problem. Without drawing it out, it's not such an easy problem. Next, we have a little classwork assignment. On the graph to the left, plot a point, and then it's asking questions so far. I want you to go ahead and work this thing out right here, Rolle's and mean value theorem, classwork. And this has you do a little sketch on this, if you can see that. Yeah, the sketch comes pretty, make your little sketches on that. So Aaron, when did you give your speech? Did you give it today? Last period? Oh, look.
Yeah, we have a big old class, so I think I'm on a lunch.
I didn't hear what you said. It was really faint, but you just look good.
Thank you. I get that one.
Can I go after this? I just thought that. Yeah.
So does that one do? Like,
Yeah, I think so.
I did whatever scenario where it's only one, two, one kind of thing.
Yeah, that was good. Yeah, that was good.
Oh, found it.
Take another minute on this.
I need my pencil.
You need to borrow a pencil?
No, I found it.
Now, I saw, what I saw in Carson's and was something like this, or what I remember from what I saw in Carson's was something like this. So he had that, and he had something like this. And then he finally had something like this.
Yeah,
That's
the old horizontal line.
Can you have one that was like this?
Is that pretty much what you drew, Carson?
I had one that was a little different, but it's still same.
Yeah, the same sort of thing.
It's cool.
Then it says, is it possible that there's at least one point on your graphs for which the derivative is not zero?
Yeah.
How is it possible? Well, it doesn't happen, okay? Your derivative is going to be zero right here, right? Your derivative is going to be zero right here. Your derivative, if you draw a horizontal line, derivative is zero everywhere, right? So it asks, is it possible that there's at least one point in your graphs for which derivative is not zero? Is that possible?
Yes. Oh wait, no.
No.
It is no, and then it said, is it possible that you draw a graph for which there is not one point where the derivative is not zero? Boy, that's twisted logic. But the first question here, no, and what does that demonstrate? What is the theorem that is demonstrated here by that question, by the answer to the question? What is the theorem that is demonstrated by the answer of that question? Starts with an R. Rolle's theorem, okay? Because the derivative is zero. That's what Rolle's theorem is. Because this, you have f of b equals to f of a, right? Because f of b is 2, f of a is 2. Okay, next we have, here's Rolle's theorem encapsulation, and then it says find that Rolle's theorem holds. Example 1, show the theorem holds between it says sketch. Does it say the between the intercepts? Yeah, well, intercepts it has to hold, right? Because you can have what is your factored form of this?
Wait, -6 and 1. No, -2, -3.
So here we have our x-intercepts, and so what is that going to look like graphed? It's going to look like this, right? So what are the x-intercepts? They're going to be 2, 0, 3, 0. Is the curve continuous? Yes. And differentiable? Yes. Why is the curve continuous and differentiable?
I don't know.
Because? Why is the curve continuous and differentiable? Because?
I would say it's what was that big word you used yesterday?
The big word, that's one.
Polynomial.
Polynomial function, right? Because it's a polynomial function and it's smooth. So we know by nature, polynomial function. Now it says, now you've gone ahead and you've figured out that it's right. It says you may now use Rolle's theorem, do so. I want you to use Rolle's theorem to find the value C that satisfies the conclusion of Rolle's theorem. And you can probably, you should be able to see what it is from a sketch of the graph. But then when you work it out, you'll prove it to yourself. Okay, so what do we know, what is our average rate of change going to be here between the x-intercepts?
1. Oh, average rate of change.
What's our average rate of change between these two? It's going to be 0, right?
Okay. Oh,
So we know that's going to be, right? We know it's going to be 0, and what is our derivative of this?
2x minus.
And so what do we do? What do we do with the 0 here? What do we do with the 0?
Set it equal to 3.5.
Set this equal to 0 here. So we have 0 equals 2x minus 5. And so work the right here. We have 2x equals 5. So x equals 5 over 2. Right? Which is visually what you'd expect it to be. Okay, so it's a pretty simple example, but this is what they look like, right? Let's see what camera here. Yeah, everything's here. Okay. Okay, find all values between the x-intercepts for which Rolle's theorem holds for the roots of this function right here. And it says confirm using your calculator.
Yes.
So I'd say f of x equals x squared times 3
So it'd be 0 and plus or minus the square root of 3, right?
Yeah. So your x-intercepts, I'm showing here, zero and plus or minus square root of 3 are going to be that. So between the x-intercepts are going to be between -3 and 0 and 0 and -3, or 0 and 3. Right, because you have negative square root of 3, 0, square root of 3. So that what you're looking for is these things in here between these. So what are you going to do? You're going to take the derivative of that, set that derivative equal to 0, and solve for x. And that's a mean value theorem type problem, except in Rolle's theorem, the case of Rolle's theorem, you're going to set that equal to 0. If it's not 0, it would be a mean value theorem application that's not Rolle's theorem. So this is what I got here. If you set that equal to 0, I'm going to get like 2. I'm going to factor out, I'll just factor out the 2 first. 2x. Then I'm going to have 3 minus, is that 2x squared? And then I want to get this thing set up right. So I'm going to write that as negative 2x, 2x squared minus 3. So what is that going to be? It's going to be negative 2x. What's our factoring of this thing here?
Oh, can that be factored?
Square root of 2x, square root of 2x, and this is going to be what? Plus square root of 3 minus square root of 3. And so that's these things, right? So we have square root of 2x plus square root of 3 is equal to 0. So we have x is equal to negative square root of 3 over square root of 2. And then we also have, we solve this one, we're going to get what? X is equal to square root of 3 over square root of 2. Does that look right?
And 0, right?
Well, yeah, but that's going to be between the x-intercepts, right?
Between them.
At 0,
Because 0 is already.
at 0, what's going to happen is you're going to just bounce off the x-axis there.
Okay.
So that's not as relevant. So what I want you to do is look in the, it says confirm using your calculator. So well, we have 3x squared minus x to the 4th. What would you get? Did you solve that yet? I'm looking around for calculators. I'm seeing a calculator here.
I get the charger again.
And we get this looking thing right here, like this. And then just to kind of see what it is, we should get square root of 3 over square root of 2, right, for that. So second trace, maximum, okay, left bound, question mark. You said McDonald's song. Who did the McDonald's song? Is that you, Hannah? That was good. That was good. It's connecting to prior knowledge. Okay, 1.2247, right?
Yep, and that's square root of 3 over square root of 2.
Kylie said that that's it. So square root of 3. The thing that I like about calculus is this. Hannah, the thing I like about calculus is this, that you can do analysis level things that without a calculator, essentially. So it takes your analysis skills to a quantum leap level, maybe a couple quantum leap levels. So I just like verifying, so oh yeah, the calculus works. Okay, let's go on to next here. And here we have the mean value theorem. It's a similar sort of thing. Okay. Here you have a situation, a verbal situation. It says you were driving a car at 50 miles per hour and you pass a police car. 4 minutes later, you pass a police car and you are traveling at 50 miles per hour. The distance between the two police cars is 5 miles, and the second police car nails you for speeding. How can he prove that you were speeding?
With his radar gun.
No, not a radar gun.
But that's not what I do.
That's not how he uses. No radar gun.
I don't think they use that.
Now you have to, the two cops communicated with each other. They knew how far they were apart. They knew when, how long it took to get there.
If I got pulled over by like 2 cops that were like scheming like this, I would just, I'd be so mad.
Yeah, you would be.
Like if they like sat there and explained their entire, like this is what they did, I would be like, you know what?
Yeah, you know what? Yeah, let's explain that to a jury in court, right? You try, the judge wouldn't know calculus, maybe.
Who says the speed limit is 50 miles an hour though? It could be like 75.
Yeah, it doesn't say that there, does it? But here's the deal, what was the average speed that car had to be making?
Oh, like, wait, if it's 4 minutes, 5 miles, wouldn't that be like 75?
Probably 75 miles an hour. Probably 75 miles an hour, because it's gonna be it's, was it 4 minutes? So 4 minutes equals 4 divided by 60 hours, 4/60ths hours. It's going to be like,
He's definitely going over 60, I know that one. Just-
yeah, that's right, because it would be 5 minutes. Yeah, so 0.06, so that's what it is.
115.
So 1/15th, yeah.
How am I supposed to show my work?
So, anyway, that's going to be the amount of hours it took. And let's see, you went 4 miles or 5 miles divided by 1/15th, right? 5 divided by 1/15th, which is the same as 5 times 15, which equals 75. So he can prove, or they can prove if they have that documentation, that even though they were going 50 when they passed, the average speed, which means probably it had to be going faster, even faster than 75 at some point, was 75 miles an hour, but they can mathematically prove. And there's another thing that you can do as a calculus student, is sometimes a police guy without sufficient information, you'll be able to, if you have contradictory evidence, you'd be able to demonstrate that and prove your, if not innocence, that you can't be nailed for it. Okay, so that's how they would prove the mean value theorem. Okay, here we have another problem here. We have this function here. Find the value of C in the interval from 1 to 5 that satisfies the mean value theorem.
Yay.
So here's one for you to work on here. Probably do that one. And what's the step? What's the step you take? First, find. Yeah, and that would be part of finding the, starts with A.
I'm sorry, what was the question?
What are you going to be finding first?
Average rate of change.
Find your average rate of
Find
change,
your A.
right? And then when you find your average rate of change, what do you do next?
Differentiate.
Take the derivative, Hannah, of the function. And then lastly, what would you do? Substitute the what for the what? Okay, I'll tell you what it is. Step 1. Find average rate of change. Okay, that's step 1. Step 2, find f prime of x. Third step,
Oh, you got to set them equal to each other.
set a rock equal to f prime of x, then solve. Solve for x. It says between 1 and 5. So here we are between 1 and 5. So what does that look like? Yeah, that's about as accurate as we get. So what are we looking for? We're looking for this looking thing here. Where does that look like it's going to be about the same?
Right after 2.
Right about 2. So that's just a reference point for you as you work this out. If we plug in 1, yeah, we would get that if we plug in. If we plug in 5, we would get that, so that's right. So what is our average rate of change going to be here?
One.
Yeah, so you have 5 minus 1 equals 1. So what is our derivative here?
All FFA members who paid their dues last year and have paid their dues this year, please report to the cafeteria. Thank you.
What is our f prime of x?
5x or 5 over x squared.
So that's it. So we set this 1 equals 5 over x squared. So we get x squared equals 5.
This is farewell, Mr. Joe.
There we go, f, okay. So x equals what? So x equals what? Plus or minus square root of 5,
But it'd be plus because it's.
but only plus, yeah, because of the situation here. So there it is, find the value of c. So c equals square root of 5. And that's going to be a little greater than 2, right?
Yeah.
It'll be more like right in 2.25, something like that. But these are really easy type of problems, I think.
How long have you been teaching the subject, Mr. T?
Let's see, it'd be about long enough to know what should be easy and what should be difficult.
No.
Long enough to know that this should be easy.
Okay, no. It's only easy, you've been doing it for so long.
No, but what is difficult about this?
Math.
Figuring out what's what.
Knowing what to do.
Knowing what to do, yes, knowing what to do. This is the part here, okay? All this other stuff is already, this stuff right here, all this stuff right here, that is what level, that is like algebra 1. This type stuff here, solving for that is algebra 1.
Oh.
Okay, now here's where the calculus comes in, but the mathematics are not difficult on this. So there's nothing in here that is difficult, other than what Gavin said, knowing what to do.